All right, so chapter 22 gets a little bit more complicated in terms of synthesis, but I think it's best to kind of come up with some basic strategies. The first class of reactions I want to review are alpha substitution reactions. So let's take a look at alpha substitution reactions. And if you remember, the alpha position is always going to be that carbon adjacent to your carbonyl carbon. The first class of reactions that we talked about were halogenation reactions. And we said we could halogenate something like a ketone. So I'll just draw a generic ketone. And in this example, let's just have a bromine installed. Oops. What reagent do I need to install a bromine at that alpha position? Acid and bromine, exactly. So we'll just have H plus and Br2. And if you look at where the bromine's installed, it's always going to come off that alpha position. And you can do this typically with ketones. And you get an alpha halo ketone. It's important to remember too, I'm going to put in a little bit of an asterisk here. What happens if we have a methyl ketone? What else can we do? So in this case, I'm reacting it at an alpha position that's not a methyl group. But if we have a methyl group, we can overshoot it and then do what?
Kick it off.
Yeah, kick it off and form a carboxylic acid. So with methyl ketones, you can do a haloform reaction to get a carboxylic acid. What reagents do we need if we want to do a haloform reaction? Does anybody remember those conditions? Yeah, so if you remember, step 1 was NaOH, Br2 in excess. And then step 2 was to reacidify it. So that's a variant of alpha halogenation that's useful exclusively for methyl ketones. We can also do alpha halogenation for carboxylic acids. So let's say we've got this carboxylic acid, and then we want to, alpha halogenate. What reagents do we need then? This was the Hell-Volhard-Zelinsky reaction. Does anybody remember that? Yeah, PBr3 and bromine. And bromine. And then at the end, we need to get rid of that acid bromide, so we just quench it with water. So this will work for carboxylic acids. But again, we're reacting at that alpha position, and we get an alpha halo acid. Make sense? The next class of reactions, instead of doing halogenation at the alpha position, we're just going to add alkyl groups. So we'll do alkylation. So let's take a look at this reaction. Actually, I'm going to change this. Sorry, guys. I'm going to do it a little bit out of order. I'll use the same example that we used in class previously, where we can install an R group in that alpha position on one side, or we can do it on the other side. Either case, this is still alpha substitution. If we want to get an R group installed on the more substituted side, what conditions do we need? Yeah, small base. So we'll use sodium hydride. And you normally run this at room temperature. I think the Klein textbook says 25 degrees C. And then second step, we're just going to do SN2 chemistry. So we'll treat this with an alkyl halide. You can't have a bulky alkyl halide. It's normally going to be a methyl or primary. And then what about the other side? What base would we use? LDA. And we want to run this at really cold temperatures. So negative 78 C. And then same thing, we'll treat this with RX in order to get alpha alkylation to occur. So that's one way to do alpha alkylation. There's also another way. This is typically useful for ketones. The other way is, let's say we've got diethylmalonate. And we want to install some sort of functional group on the alpha position. What reagents would we need in order to get this alpha substituted carboxylic acid? Yeah. First up, we have to use sodium ethoxide. Why don't I use sodium hydroxide? What was that? Yeah, that, and we want this ethoxide to match the leaving group coming off of our ester. You always want to try to pick the corresponding base. And then after that, we're going to treat this with our alkyl halide in order to get the substitution to occur. And then how do we do the last step where we convert the ester to the carboxylic acid and then we lose the other half of the molecule? Yeah, acid and heat. So this is a pretty simple reaction, and in this case, essentially, all you're doing is gaining this entire portion of the molecule and substituting the alpha carbon. If we want to do the same thing, but with a ketone, we can. We do sodium ethoxide, followed by our alkyl halide, and then we do hydrolysis and decarboxylation. But in this case, you'll get a methyl ketone, and you'll get alpha substitution off of that methyl ketone. So in this case, instead of using diethylmalonate, you want to use ethyl aceto acetate. But just like in the other example, essentially all we're going to do is add on that ketone, specifically a methyl ketone. Make sense? I think that's it for the alpha substitution, but we did cover a couple of reactions for beta substitution. So let's make another list for how to make beta substituted molecules. All right, with beta substituted molecules, it's pretty straightforward. We just covered a reaction in our pod where we can take a conjugated ketone or an aldehyde, and we can add in some sort of group onto this R position. And actually, let me make this R prime. How would we get this substitution to occur? Or addition, in this case. Does anybody know? Let's say that R group is a methyl group. Can I use a methyl Grignard? Yeah, we can't use a methyl Grignard because it will add into the ketone, but in this case we could use Gilman reagent. So R2CuLi, that's a much more gentle source of carbon. And then we can treat this with dilute acid in order to quench this. It is important to remember with this that any stabilized enolate or enamine will do this. Or carbanion will work. So we saw in the storic enamine synthesis that if you have an unstable enolate, the trick is to turn it into an enamine, and that's a simple workaround. So in this case, we're not adding to the alpha position, we're adding this R group onto the beta position. All right, just a couple more reactions. The next one that we have was if we treat an aldehyde with sodium hydroxide and water, we'll get an aldol reaction. And if you remember, in the aldol reaction, what you're actually getting out is an alcohol that's beta to your carbonyl, in this case the aldehyde. So this would be a beta hydroxy aldehyde. Typically we see aldol reactions done with aldehydes, but you sometimes see it done with ketones. And then what happens if we apply heat to this? Yeah, condensation. So we can further derivatize this and get our condensation product. However, that's not really the same. So we'll just do this in brackets. All right, and then we can do the same thing with esters. This is the Claisen condensation. This is with sodium methoxide and water. However, this time all you get out is a beta keto ester. So now we've got a ketone in that beta position instead of a hydroxy group. I'm not going to go into all of the variants of these reactions because the Diekmann cyclization, the Robinson annulation, all of those are kind of variants on all of these. They're just intramolecular versions. But this is a pretty good review of the reactions that we've covered this chapter. One thing a few students asked for was they said, can you get me some fill-in-the-blank study guide stuff? So I put that in a section in the notebook. So this is good review to quiz yourself on. The first one's about forming enolates, and then it looks like we've got some aldols, some practice questions, and so on. So this is really good review. I also added that in for chapter 21 as well, so if you want to review for chapter 1, just open up the notebook. And then if you just want to print out a quick study guide, you have one in the back of all of your chapters, but I've also included a section in the notebook that has a really quick and useful study guide. Does that make sense? All right, make sure you guys don't put this off until last minute. Please don't study the morning before. Try to get your studying done today and tomorrow. Yep. The what?
The one where you add ketone.
There you go. All right, so what we're going to do with the rest of the class period is we're going to work on that packet of problems. Tomorrow we're going to do more synthesis problems, but I want you guys to work in groups. If you're stuck on a problem, help one of your teammates or your classmates that doesn't understand. That will help both of you guys out. And try to draw full mechanisms if you can. I know you might run out of space, but pull out scratch paper if you need to. Oh, shoot. One other small thing. I made a typo, because that's common. Right here, it should be O2. I think I didn't have the 2 on your guys' printout, and I corrected it for the online version. So just add in the 2 there, and that will make the problem a lot easier. All right, so if you guys want, you can push tables together and work in groups, and then I'll come around the room and help you guys out.